Hey everybody, welcome to Unit 6. This is one of my favorite units. It's all about right triangles and their properties. I know you're probably sick and tired of triangles since we've been doing it since Unit 3, but this one is my favorite. We are going to start by doing the Pythagorean Theorem, which is something you've been using for quite a few of the practices, so we're just going to review it a little bit. But before that, we want to simplify radicals because we're no longer going to get into decimal answers with these and some of the stuff for future lessons. So let's review how these are done. So when you're giving a radical, there are many ways that you can simplify this, just depending on how you learned it. I'm going to show you one way, but that doesn't mean that's the only way. But the way that I like to teach it is I take a look at the numbers that are given underneath the radical, and I try to determine, well, what's the biggest perfect square that exists? Perfect squares are numbers like 4, 9, 16, 25, 36, 49, and so on and so forth. So when you're looking at the numbers, you want to say, okay, what's the biggest perfect square that's going to go into that number? For example, 72. So I look at the next number down, which is a perfect square, which is the number 64, and I work my way down until I find one that actually divides into 72. And the first one that works is the number 36. And so what I like to do is break this down into two numbers. So the square root of 72 is the square root of 36 times 2. So 72 is 36 times 2. It's just a basic breaking down, factoring into two numbers. Well, the nice thing about this is that radicals can be broken apart. So this is the same thing as the square root of 36 times the square root of 2. Well, you know what the square root of 36 is. The square root of 36 is the number 6. Now, the square root of 2 does not have anything to simplify down further, so it's going to be just the square root of 2. And so this is a radical simplified. We have 6 times the square root of 2. Now, on number 2, we do things a little bit differently. Since there's a number on the outside, we have to take that into account. However, we've already broken down the 72, so we know what that's going to turn into. So we have the square root of 36 times the square root of 2. So at this point here, we still have to remember that there's that 2 there. And so when I take the square root of 6, I'm going to multiply it by the number on the outside, because this is just one big multiplication problem here. This is 2 times square root of 72. And so when I simplify it, I continue with that multiplication. So 2 times 6 is 12, and then I have the square root of 2 afterwards. I can't go any farther than that because one number is in the radical and one number is not. So since we're doing Pythagorean theorem that involves squaring things, we need to know how to square a radical. So I have the square root of 7 squared. Now keep in mind when you're squaring something, that means we're essentially multiplying it by itself. So we're kind of going the opposite way as you did the top one. While I broke it apart, this one I'm going to put together. Square root of 7 times the square root of 7 is the square root of 49. Well, that's a nice perfect square. The square root of 49 is 7. And so this one's nice and easy when there's no number in the front there. The square and square are inverse functions of each other, and so they essentially cancel out. Just like plus and minus or times and divide are inverses of each other, square root and square are. Now we have to be careful with ones like number 4, because you have to keep in mind that this is doing 3 times the square root of 7 times 3 times the square root of 7. And so when you're rearranging things around, there's a 3 times the 3 out here to get 9. Square root of 7 times square root of 7 ends up being 7, because that's what we did in number 3. And so we're going to multiply those two things together to get 63. So the biggest thing here for number 4 is keeping in mind that you're squaring the number 9, or number 3. You're not just going to do 7 times 3, or even just 9 times, well, you are doing 9 times 7, sorry. Okay, so just keep that in mind moving forward, all right? So let's do a quick review of the Pythagorean theorem. You're given a right triangle. The A and the B are going to be both the legs, and C is the hypotenuse. And the big idea is it's A squared plus B squared equals C squared. Officially, if it's a right triangle, the sum of the squares of the sides is equal to the hypotenuse squared. And so the C value here is always the hypotenuse. It's always what's across from the right angle. It's always the biggest number. Remember, across from the bigger angle is the bigger side, which is why that number that's always biggest goes for C. So let's just go ahead and review those really quickly. There's a couple, I just have 3 examples here, very straightforward. We know that it's x is going to be the hypotenuse, so when I start substituting values in, it doesn't matter which one's A or B. What matters is what C is, and this problem is the x. So I substitute it in, I square it, I add them, and then I take the square root. So that one was nice and easy because we had a bunch of perfect squares. If you didn't understand that process, please make sure you're asking. However, we have been working with Pythagorean theorem. So taking a look at the next one here, I see that x now is a leg instead of a hypotenuse. So I'm going to now put the x as A or B, it doesn't matter, and C is 5 because that's across from the right angle. In this case, I'm going to square them and subtract them, and then take the square root. So note the difference. In the one on the left, I give hypotenuse, so I add them, and the one on the right, I need to find a leg, so I subtract the numbers. All right, so those are nice, pretty, perfect numbers. So let's do some numbers that weren't so perfect. So let's go look at this one here. Again, I'm looking for the hypotenuse. So that means I'm going to leave the c as c, or in this case, I change it to x. So substituting in 4 and 6, doesn't matter what order you put them in. I could have done 6 squared plus 4 squared. So I square the numbers and I add them, and I'm going to take the square root. Now the thing about this is that 52 is not a perfect square. And so we're going to do like we just did a moment ago on the previous slide and break it down. Well, the biggest perfect square to go into 52 is 4. So this simplifies down into 2 square root of 13. So again, radicals are going to be our answers. We are not accepting anything with decimals unless otherwise specified. Okay? All right, just to take it one step further, we're going to have quite a few problems that look like these. So we want to use it to find the area. The first thing we need to do, though, is find the height of this triangle, because the area of a triangle is 1/2 base times height. Since it's an isosceles triangle, we know that height there is going to break that top in half, so that's 15 and 15. And the height we're going to call h. And so I'm going to kind of look at one triangle here, and I see that I have 15, 18, and h, where h is a leg. And so I'm going to use Pythagorean theorem to solve for it. So h squared plus 15 squared equals 18 squared. Square them, subtract them, square root them. Now, once again, this is not a perfect square of the 99, so you have to kind of simplify it. This is 9 times 11, so it simplifies to 3 square root of 11. So now that I know the height, I can go ahead and replace that. So let me go ahead and erase everything that I just wrote in here. We can replace that h with the 3 square root of 11. So now I'm done with all that. My focus now is finding the area. Well, again, area is 1/2 base times height. Think back, though, the original base was 30, not 15. So it's 1/2 times 30 times 3 square root of 11. And with multiplication, we multiply kind of like when you multiply with x's here. You would do 1/2 times 30 times 3, and then kind of let square root of 11 tag along. And so when we do that, we multiply 15 times the 3 is 45 square root of 11 feet squared. If you didn't follow that, again, please hit pause, ask your teacher for questions. Make sure you're understanding why we're putting things in and how to multiply these things together. Okay? All right, why don't you go ahead and hit the pause button and try this problem out on your own, and I will give you the answer in just a moment. Okay, so for this one, what we end up here is a height of 24 and an area of 240 meters squared. If you didn't get that, ask your teacher. All right, so in some cases we have perfect squares, and other ones we don't, in the sense of we have some that had to become radicals and then some that aren't. And so just so you're aware, we have these things called Pythagorean triples. And these are the most common ones that exist, but there are tons more. The one that I would encourage you to remember is the 3, 4, 5 triangle, or the first one here on the left. That means that if you ever see a 3 and 4 as a leg, you automatically know it's going to be a 5 for the hypotenuse. Some other common ones are 5, 12, 13, 8, 15, 17, 7, 24, and 25. So these are all going to be legs of a right triangle and a hypotenuse of the right triangle. And the nice thing is also that their multiples are also going to be perfect for the Pythagorean theorem. Like if I put it right in there, that's going to work. So just kind of keep that in mind. Any multiple is going to work. Okay? If this kind of went over your head, don't worry about it. It's just kind of, it would help you solve problems faster by being aware of these patterns. Some of the first couple ones of the examples had those, so just keep aware of that, okay? All right, so now let's kind of take a look at that in relation to other triangles. So with right triangles, a squared plus b squared equals c squared. If I put those numbers in, it's going to be equal. So let's look at an acute triangle. I have 6, 7, and 8 for our values, and let's put it in. Now 8 is always going to be, or the biggest number is always going to be c, so that's what I'm going to put into c squared in my Pythagorean theorem, and let's see what happens. So I'm going to put a squared and then 6 squared plus 7 squared. I square the values and add them, and I end up with this. So what I'm noticing here is the value of c squared is smaller than the sum of the other two sides. So let's do the same thing now with an obtuse triangle. And so kind of think about it. What do you think is going to happen before I click through these slides? And let's see if you're accurate, okay? So once again, we go off of the biggest side, which is 38. So c squared, how does it relate to a squared plus b squared? C is always the biggest. So I get 38 squared, then 25 squared plus 17 squared. Square them and add them. And I see here now that c squared is bigger. So this is the converse of the Pythagorean theorem. You're used to seeing c squared is equal to a squared plus b squared. Now we're going to do the converse. Everything is in relation to C. If C is equal, it means it's a right triangle. If C is less than, that means it's an acute triangle. And if C squared is bigger than everything, then it's an obtuse triangle. So these are just some extra things to kind of be aware of to figure out what type of triangles we have. So again, everything relates to C squared. Let's do a couple of examples with that. Okay, so let's look at letter A here. I have the numbers 9, 15, and 3 squared root of 34. Do you see how right underneath there I have this, which is about 17.49? The purpose of that is for you to help you decide if this actually forms a triangle or not. Remember, you always need to check to make sure that two sides add up and are bigger than the third side, and that's the purpose of changing it to a decimal like that. Otherwise, when you put it into Pythagorean theorem, don't do that. Also helps you to determine which one's going to be C. So in this case, 3 squared root of 34 is our C. Okay, so this forms a triangle, so we substitute it in. 3 squared root of 34 squared, and then doing 9 squared plus 15 squared, I get 306 and 306. This is equal, therefore I have a right triangle. And that's the process that you're going to take. Substitute it in and compare the values that we get. So for letter B, same deal. We get 676 and 653. Based upon that, it's a greater than, therefore it's going to be an obtuse triangle. Always put the biggest number within. Go ahead and try C and D right now. Okay, for letter C, you would have gotten 61 and 61, which means it's equal, so it's a right triangle. And for letter D, you would have gotten these two values here, which is an acute triangle. So if not, make sure you're getting that help, okay? All right, last but not least, we got some word problems. We want to know how high up on the wall with a 20-foot ladder would reach if the foot of the ladder is placed 5 feet away from the wall. I'm sure you've heard of these problems before. So let's go ahead and label everything on this triangle, because when you don't have a picture, it's always best to draw a picture. So here's what I know. I know the ladder is 20 feet, which is why I label it as such, and the distance from the wall is 5 feet. I'm trying to figure out how high it is. Okay, so we know that there's a right angle here. This is just a glorified Pythagorean theorem problem. The hardest part about this is translating it from the word problem to the picture, so just keep that in mind. All right, so let's plug it in. We got 8 squared plus 5 squared equals 20 squared. Square the numbers, subtract them, and then take the square root. Remember, we're always not going to go into decimals, so we're going to find the biggest perfect square, and 375 is the number 25, so we break it down and take the square root. So our final height is 5 squared root of 15. I'm sure you can do this and get the decimals, no problem. The other hard part about this is simplifying those radicals. So if you need some help with that, I'm happy to give you some more practice on how to do that, okay? All right. Last one. A flagpole cracked 9 feet from the ground and has fallen as if hinged. The top of the flagpole hit the ground 12 feet from the base. How tall was the original flagpole? Okay, so what we know here is that there was a flagpole that broke over. So we have a height that's still standing of 9 feet. I don't know how much has fallen over, but I know that the very top here is 12 feet from the base here. So we need to figure out how tall or how long this piece is right here, and then add it to the piece that's still standing. So there's a broken flagpole going on here. All right. Once again, it's a lovely glorified Pythagorean theorem problem that you saw earlier. So let's go ahead and solve using Pythagorean theorem. 9 squared plus 12 squared equals 8 squared. Square them, add them. This is a nice perfect square, so the square root is going to be 15. That means the fallen piece is 15. So I have myself a flagpole. I had a portion of 9 feet there. A 15-foot had fallen. So we're going to take the pole's height and add them together. 15 plus 9 is a total of 24. Whew! That was quite a bit to learn, huh? I'm sure you're very comfortable with the Pythagorean theorem. Like I said, we've been using it in class. The new stuff is probably the converse to the Pythagorean theorem, as well as simplifying radicals. So if you need some extra help, please don't hesitate to let your teacher know you just want a couple more examples when it comes to those kinds of problems, all right? And get to the practice. Take care.